Yeah, so we're gonna be looking at these questions. Where question 1, they say that we should determine if the following examples obey the laws of closure, the law of associativity, commutativity, identity, and inverse. And then these should be applied on natural numbers, integers, rationals, and real numbers when we are given this equation. A star B is equals to AB over 17. So our binary operation here is a star. Then on question 2, they say we should define this O on R as A or B is equals to A 7, AB over 15 for all AB element of R. And they say, does this binary operation define the law of identity? Then question 3, they say we should investigate if the operation hash defined on R as A hash B is equals to AB squared for all AB element of R satisfies the law of identity. And then question 4, we are asked to check if the following statements are true or false. Remember, this question 4 is coming from predicates in SMTA022 and also SMTA022, right? So you are expected to know such questions, so they can still bring such questions in a multiple choice because you're expected to know them. You have learned about them. So we're gonna first go through the first one, which is to determine if the following examples obey the law of closure. But we are given this binary operation. They say the binary operation is A it's A star B is equals to it's 5, right? 5AB over 17. Then they say we're given this, right? The binary operation. So they say that we should check whether these laws are satisfied on this. So yeah, let me check if it's really 17. Yeah, I think it's 17, right? 5 or yeah, over 17. So they say we must check this here if the binary operation satisfies this condition. So first thing that we're gonna do here, we're gonna check closure. We check closure on, they say we must check this on natural numbers. We check this on integers. I'm just gonna write them anyhow, right? Then we check this on rational numbers. And yeah, I think lastly they said we must check this on real numbers. So first we're gonna be checking closure. We check closure. We check closure. So first we'll check closure. So every time when we check closure, right, we are saying that in this case, let me just say closure on a natural number. First I'm gonna check closure on natural number. I also check closure in Z, closure in Q, closure in R. So I'm gonna check all the closures, right? So now we're supposed to check closure on N. So every time we're checking closure, right, we're gonna have to take two elements arbitrarily. You see, right now? So it means that I'm not gonna take numbers. I'm just gonna take variables A, B, which should be an element of the set which I'm dealing with now. So this is going to be an element of a natural number. You see, right? So since I took this, I applied the binary operation. I want to check. I say that now, if I have A star B, which according to this, it's supposed to be what? It's supposed to be 15. It's 5, not 15. AB over 17. So I ask myself, right, is this an element of a natural number? Is this an element of a natural number? You can tell me, does natural numbers have denominators? Are they in this form? Are they in rational form? Natural numbers? No. So it means that this will not be an element of a natural number. We say, right, so since this will not be an element of a natural number, so we can check this by counterexample. We've also learned counterexample in we say proof by counterexample. We've learned this proof by counterexample in SMTB000 and SMTA012, right? The previous level. We've learned this counterexample that when we are using counterexample, counterexample is usually to prove that something is false. We say right now. So even now we take two numbers. Let's say by counterexample, we let A being equals to 2 and B being equals to 5. We say right now, when I let A being equals to 2 and B being equals to 5, or I can take this to be 3. When I take this, then I come here and say 2 star 3, which is equals to 5 on A I substitute 2, B I substitute 3, all over 17. And what do we get for this? I know that 5 times 2 is 10, times this is 30. So this will be 30 over 17. Is 30 over 17 an element of a natural number? No. We agree right now. So this won't be an element of a natural number. So we can now come and deduce, since we've shown here by taking an element arbitrarily, and also we've shown by counterexample. Alright. So it means that now we can come and say therefore closure is not satisfied. So I can say that this closure is not satisfied. We're dealing with that initial number, right? In N. We say right now. So closure is not satisfied in N. So now we check closure in Z. So now I want to check closure in Z. Let's check closure in Z. Now we check closure in Z. Now, for us to check closure in Z, let me do this. Now, for us to check closure in Z, we're gonna do the same thing. We're going to pick two elements. We always pick two elements, A, B, which is an element of Z. We say right, when we pick these two elements, we check, we say A star B, which is equals to, it was 5 AB over 17. Can this be an element of an integer? Will this be an element of an integer?
No.
No. Then this won't be an element of an integer. Because also integers do not have what? Do not have denominators, right? The only denominator they have is 1. So this one is 17. So it means that here, the same thing which we've done here, see, we will say that this is not an element of this, and then we check by counterexample. We say proof by counter. So we're only going to use counterexample if this is not an element, if this is disproved, you say right now. So remember, counterexample is used to disprove. Proof by counterexample. Proof by counterexample. So we're going to let two elements. Remember, we can take A to be something, B to be something. So in this case, let's let some different values here. We let A be equals to 1 over 2 and B equals to minus 1 over 2. So now since we have this 1 over 2 and minus 1 over 2, we can come now and say 1 over 2 star minus 1 over 2, which this will be equals to 5, 1 over 2 minus 1 over 2 all over 17. We say right. And this, if we check, what is it going to give us? Let's check with the calculator. So this is going to give us minus 5 over 6/8. And this is not an element of an integer. We agree right now. So this can either be a real number or a rational number. So we agree that now we can come in and give the same conclusion like this one here. We say that therefore closure is not satisfied in Z. So next thing what I'm gonna do, right, I'm gonna check closure in this, then yourself you're gonna check closure in R. So I'm gonna leave you with one question to go do that, even though you guys don't send, because you find 3 people sending the solutions. So now we're going to check closure. Yeah, the best way to make it in this one, you must participate. Here you must participate here, because it's a lot of theory. So the more you participate, the more the theory gets into your head, then you can be able to remember it. So now we're checking closure in Q. We're gonna do the same thing. We let A, B be an element of Q, right? Then we apply our A star B, which is equals to, now this will be equals to 5AB over 17, and this will always be an element of a rational number. We agree here, right now? Do you agree that this will always be an element of a rational number?
Yes.
Yes, so it means that now we know that this will always be an element of a rational number, because rational numbers are the ones which have A over B. So this will always be an element of a rational number. So there's no need for us to check by a counterexample on this one, because it's correct, right? Counterexample, we can use it to disprove. So there's no need for us to check counterexample with this one. So closure in this is satisfied. Therefore, closure. Let me say, I can say, yeah, closure. I just remove not. Is satisfied in Q. We say right now. So you'll try. Let me say try closure in R. So you'll try closure in R, right? So now we go back to the question. They said we must check if these laws are satisfied. Closure, laws of closure, associativity, commutativity, identity, inverse. So here's the thing, right? So the idea is not to check them both one by one. You see right now. What you do first, what I was doing here now, let me explain what I was doing. I first check closure on the end. If closure is not satisfied, there's no need for me to check this. You see right now, there's no need for me to check associativity, commutativity, identity, or inverse in that set. That's why I skipped it. I skipped this, and then I went to the second set, check closure. I found that still it's not satisfied. You see right? I checked N, I found that it's not satisfied, and then I move. I check Z, it's not satisfied, I move. Then now I check Q. I find that Q is satisfied. So it means that now since closure in Q is satisfied, I can now check the second law, which is associativity. You see right now? So I can now say associativity in Q. You see right now? Now I can check associativity in Q, because closure is satisfied there. Then for associativity, I'm always gonna let 3 elements. Here you always let 3 elements. Let A, B, C be an element of a rational number. So when I let this be an element of a rational number, the aim now is for me to check the left hand side and the right hand side. Remember, this is supposed to be like this. You know, you're not supposed to write this, right? It's supposed to be A star B star C, which is equals to A, according to associativity, star C. Though you're not supposed to write this. So what you're supposed to do here, you're going to take this side, show it. You see right now, I'm going to show one side and then show the other side, and then I'll decide if they're associative or not. Remember here, initially we're given that A star B is equals to 15, not 15, 5, man. Why am I always saying 15? 5 AB over 17. You see right? So it means that here, what I must do, so I think here it's going to be simple if we start with the one that we're given, right? So we can start by checking this one. Yeah, because now it will just be simple for us to come and plug. Inside brackets, we're just going to plug 5AB over 17, because we know that this is equal to 5AB over 17, right? Star C. So what this tells us, remember from the first session which we had, I said that now, remember, I'm going to associate these two. The star says that whatever that is, you see, according to this definition, says that whatever that is comes before the star will be substituted on A. Whatever that comes after the star will be substituted on B. You see right now? So now, here, I'm going to do the same. So I'll take that equation. I'm going to say, here, I have 5. Then on A, I'll substitute this entire thing. You see right now? So on A, I'll substitute that entire 5AB over 17. Then on B, I substitute C. You see right, on B, I substitute C all over 17. Then this will be, that will be 5 times 5, it will be 25 ABC over 17 over 17. And this will be equal to, so this will be, what is 17 times 17 to be 25 ABC over 289. Yeah, then we'll have this. So now the question is this an element of a rational number? Yes, it is, because we know that already, that we know. We've checked that closure satisfies. So whatever that will be getting inside here will always be an element of a rational number. You see right now? So that's why it was important to check closure, so that we don't have to check here, is this an element of a rational number? This will always be an element of a rational number. You see right, since closure is satisfied. So it means that now we know that this is an element of a rational number. So there is no need for us to say this is an element of a rational number, because we've already checked closure, right? So now we just check the other side. The other side, which is A star B star C. Then we must check if these sides are going to be equal. You see, right? Then according to that definition, you see we have B star C, right? The definition comes here and say this. So let me just do this. I'll write the definition first here. Definition says A star B is equals to 5AB over 17. And what we have here, we have A star B star C, right? And what we see here is this, is that A will map with B, B will map with C. So it means that where we see A, we're going to plug B. Where we see B, we plug C. So this is going to be A star, then we have 5BC over 17. So that where we see A, we plug B. Where we see B, we plug C. Then this will be, now when we compare this, you see now we're going to compare this now. When we compare these now, we realize that A will remain A, right? So on that equation, this will be A remains A. Then B, on B, I'm going to plug 5 BC over 17. You see right now, over 17. Then this will be equal, so 5 times 5 is 25. A times B times C is ABC over 17 over 17. And this will be 25 ABC over 289. We say right. When we check, the left hand side and right hand side are equal. You say right. So it means that associativity is satisfied. So we can just conclude here to say A star B star C is also A star B star C. Alright, so since this is the case, we can now conclude that this is satisfied. So now we can say, therefore, associativity is satisfied in Q. Right? And then for safety, even though it's not important to write this, we can just put it there. And then we keep it like that. we know that these are an element. Did I write not an element here? Yeah, so this is an element of Q. Yeah, satisfied in this. So now let's see, everything is fine now. So now this we see that associativity is satisfied, right? So now we can check commutativity. So now we come and say commutativity in Q. And then now we say that we're going to let, for commutativity, we let two elements be an element of Q. And then the aim of commutativity is to show that A star B is equal to B star A. You say right now. So here we can just show A star B. A star B, we know that A star B is 5AB over 17. Then if we apply B star A, we're going to replace A by B, we replace B by A. We see that these two are still going to give us the same thing. You say right now. Hence, here we know that A star B is equal to B star A. You say right. Multiplication commutes. So this is still going to give us the same answer. So now we come and say, therefore, commutativity or commutative law is, or the law of commutativity is satisfied in Q. We say right now. So we're done with commutativity. Remember, after doing commutativity, now we can check identity. I'm sure we agree with that right now. So now we can check identity because commutativity is satisfied, associativity is satisfied. So now we can check identity. So, because yeah, let me check. I think that's what we are told to check there on the question. Yeah, after commutativity, we must check identity. Then remember, if identity is not there, we can check inverse. You say right. You say right now. So if we find that's why we need to check identity before inverse. So if we find the identity, it means that we can check the inverse if it's there. So now we come to check identity. Now when we come to check identity, now we realize that for identity, let me say identity in Q. We have this. For identity, we must come and let one element be an element of Q. So when we have one element being an element of Q, this should happen such that we should let A be an element of Q such that A star E will be equal to E star A, which is equal to A. You say right now, when we apply an identity to A, we should always get A. You say right, it doesn't matter whether we apply it on the left hand side or the right hand side. So we must show both of them. So we're going to show both of them to check if they are applied. So let's check. We check this one first and then we check this one and we'll see if we're going to get it. Now, when we check A star E, this according to the equation, it says, remember the equation says that A star B is equal to 5AB, right? So this will be 5, it means that B will be substituted by A, 5AE over 17, which this will be equal to A, which this will imply, right? This, we must check this being equal to A, then we also check this being equal to A. So that's what we must check. So now, this, we're going to say that if I want to find this E, right, I'm going to multiply the other side by the inverse of this. So E will be equal to A times 17 over 5A. And the A will cancel out, right? Then here I'm going to get 17 over 5. And that will be our identity. So Is 17 over 5 an element of a rational number? Is 17 over 5 an element of a rational number? Is this an element?
Yes.
Yes, right. So this will be an element of a rational number. So now we check the other one, which is a star a, which will be equals to, this will be 5a over 17, which is equals to a. And if we check here, if we apply this, we're still going to get the same thing, right? We're still going to get that a is equals to 17 over 5, which is an element of a rational number. Hence, a exists, right? And a will be equals to 17 over 5, because we've checked that. And we're gonna say that therefore, let me say therefore, we're going to say therefore identity is satisfied in Q. We said, right, identity is satisfied in Q. So what we're left with now is to check the inverse, right? We're supposed to check the inverse. Yeah, I think, let me see. I thought I had checked. I think it's because of these ones here that they with a long space. Should have added an extra page. So now we say that we're supposed to check what now? We're supposed to check the inverse, right? So for the inverse, let me erase one thing here and then I'll cancel it after. So for the inverse, let's check. We can erase this. Let me do this first. Yeah. So now I want to check the inverse of that. So for us to check the inverse, right? For the inverse of that, we're going to come and say, now, they should be this. Wait, I'll be back now. Yeah, I think we can continue now. So for the inverse, we must come now and say that. So let me say we are going to say, for this inverse, we're going to say, let's say we let A be an element of Q. All right, now. So when we let this A be an element of Q, because here we're dealing with a Q, we agree, right? So it means that for us to come and show for the inverse, right, we must show, so what we must show, we must show that A star A this is equals to, let me even say this, which is equals to A star A. So here, this you can put it here or you put it in the middle. It's also fine. So this is what we must show, right? For us to get the inverse. So we're going to check both of them and see what we get. So we first check this one. We know that when we have A star A this will be equals to 5. A will remain the same, it won't be replaced, right? But B will be replaced by A inverse. So this will be this over 17, right? Which this will be equals to, and what do we get here? When we plug this, we can tell us what do we get. And let me see what we had down there. Yeah. What do we get here? What is the solution here? Anyone who can tell us? This will be what?
17 over 5.
To be 17 over
5.
Over 5. How did you get 17 over 5?
Because on identity, our E is 17 over 5, right?
Our E is 17 over 5. So you're saying that, or let's do it like this so that it can be simple, right, for everyone to see. Let's say this is equals to A, right? And then we start implying, then we apply them both sides, right? Let's say we remember we had A 5, then you're gonna have this, right? Which is over 17. Which this is equals to, our A was what? Was 17 over 5, right? So now the aim is to find this one. So this is 17 over 5, correct there. That means that now what you're going to do, you're going to multiply both sides by the inverse of this, because we must make A's inverse subject to the formula. You see right now? So we're going to say this is equal to 17 over 5 times the inverse of that will be what? 17 over 5A. We agree here right there. So this will be the inverse of this. And then what does this one give us? Remember 17 times 17 that time gave us 289, right? This one 25A. Let me check, let me confirm this. Yeah, it's 289 over 25. So that this A doesn't look like 9, right? Yeah, so we're going to have this. Now, we see that this is our inverse. So the aim was to find an inverse. And this is an element of a rational number. We agree, right? So it means that, therefore, now what does this tell us? Is the law of inverse satisfied in Q or not? Is the law of inverse satisfied in Q or not? It is, right? So, because this is an element of Q. Right. That's somewhere we're concluding like this to save space. In Q, right? Why am I saying that? Remember, before I could decide this is satisfied, I should also check the other side, right? Which is A, this, star, A, which is equal to E. And then when we check this, we find that this is 5 A inverse A, but this is multiplication, but I believe that multiplication Q modes, and these are the same. So here still we're going to get that this will be equal to 17 over 5 times 17 over 5A, and this will be equal to 289 over 25A, which this is also an element of Q. We say, right? So we agree that these two are the same. Therefore, the law or the inverse is satisfied in Q. The law of inverse is satisfied in Q. Hence, now check this. This tells us something. When these are satisfied, when all these are satisfied, you can say something about this star, this binary operation. If closure is satisfied, associativity is satisfied, identity inverse. You see this four. Let's start with this four which are marked. If these four are satisfied, excluding a commutativity, right? When we exclude commutativity and we focus on this four, we say that star is a group. You say right now, if they are satisfied. Now, when we come to say that also commutativity is satisfied, then we say that this is what? This is an abelian group, right? Then when they are just 4, it's a group. When now commutativity is also satisfied, they're called an abelian group. So star is an abelian group under under rational numbers. So you yourself, you can check real numbers. So when we come here, they say define this on R, right, as A or B is equal to this for all. This does this define the law of identity. Now let me tell you this with this one, right? So you're gonna be writing question 2 as an exercise A. So what you're gonna, cause I said that you must check this, right, R, if it's a closure or not. So I won't do this one because I'll be giving you a solution there. So what you do here, you're going to check closure first before you can check an identity. You check closure. So here's the hint. You're going to check closure under R. And then after checking closure, this is an identity. You can check it. You can skip to identity. This binary operation doesn't have to satisfy associativity, commutativity for each to satisfy identity. As long as it satisfies closure, it can satisfy identity. Is that right? So you must know that this one is independent of these two, even though they are all dependent on closure. So this identity is independent of these two. It only depends on closure, and also inverse depends on identity and also closure. You say right? Then these two only depend on closure. You say right? Then we check identity in R. If this is satisfied, it means that therefore it is defined. You say right? So that will be the case there. Then on this one, we investigate if the operation defined on R, this is also R, for a B element of R satisfies the law of identity. So it's similar thing to this one. You're gonna do the same hint, right? You do the same thing, you check closure, then you check identity. And then with question 4, now let's come to this one. With question 4 here, they ask us, they say for all X element of R, let's say we take all X. Let's say we come in a, let me draw a circle. We come in a pool of real numbers. We say that for all X values here, right, that are an element of R, there will exist some Y value such that when we multiply here, remember R's consist of rational numbers, right? 1 over 2, this type of numbers, right? Then when we come here and say there will exist some number there, which is an element of R, right, which is a Y, that number, such that when I multiply X and Y, I'll get 2. Does that number exist here? Let's say I take 2 here. Let's say I take 2. Let's assume that I take 2. Let's say X is equal to 2. Is there a number that when, so I can say this, right? Is there a number that when I take this X being 2, 2Y is equal to 2. When I divide both sides, I'm going to get that Y is equal to 1, right? Obviously, there will be this number there. So this number will always be, it doesn't matter whatever I take, right? Real numbers consist of all numbers, all the definite numbers, excluding complex numbers, right? Those ones will come to there. These real numbers consist of negative, positive, root, rationals. So this will be what? Will this be true or false? Let's check if that number will exist. And another thing, so before we check those numbers, right, the first number that we take first, let's see what you're going to check, right? You check the first numbers which you can check in most cases. You check this. You're going to check 0. Then you check other numbers. You see, right? Those ones we're just gonna take random. So let's say this here. Remember mathematical induction, right, tells us that I can take one number, then I take k, then I take k plus 1. Alright? Then I can take minus k, I take minus k minus 1. Right? So let's check. When I take 0 now, remember I can take these ones will always satisfy the condition, right? Any number they will always satisfy, because if I take 1, I'll always find that there's 2 and y, that will give us 2, right? Then if I take 1 over 2, I'll always find another number, which is 4, which will always give me 2. So whatever number I take, they will always be correct. But let's say if we take 0, let's say I take x being equals to 0. Is there a number that when I apply here, does this number exist in R? Is this number an element of R? No, right? Ne? So this is not an element of R. So if I take x being 0, it won't work. So always when you're given these questions, right, consider 0 first, if it works. If 0 works, it means that these other ones might work. You said that if they said for all, first if they started with for all, if you take all these numbers, let's say take 0, can there be such a number? You said right. Then, now, with this one, I used to call this one, remember, this one, it's a universal set. Then I used to call this one is an existential set, right? I used to call this one no restriction. In SMTA022, I call this no restriction. Then I call this one restriction allowed. Restriction allowed. So here, restriction is allowed, and on this one, for all is not allowed. So whenever your statement starts with for all, just know restriction is not allowed. You can't restrict yourself to certain numbers. You must consider all numbers, right? And then always try to check the one which can disprove. So I try to find the 0. Find that 0 usually disproves in most cases. These ones, you're just going to take in. So now we say that if I get 0, this will be false. So it means that this statement is false. And you must give a reason, right? It's false for x being equals to 0. Now, when I come here, this one, they say restriction is allowed because it started with they exist. So when it starts with they exist, in other words, you're going to restrict yourself, right? You are going to restrict yourself to say that, let's say, here I take 2. When I take 2 here, let's say I take 2, right? I take 2, myself, I'm saying that if I take 2 from R, these ones are going to come randomly. Is that right? Nice thing about the first one is that here, the statement can usually be true. Reason being, this one, the number is going to generate first, right? Randomly. Let's say this thing generates 2. Yourself, you can look for a number that can multiply that 2 and give you 2. Is that right? But here, the reason why it became false is because now the number generated 0. And there's no number that we can multiply there to give us 2. So that one was false. So with this one, yourself, you first choose a number. They'll exist. So I'm saying that they'll exist 2. If this one comes and generate 0, is that right? Still, it will lead us to the same conclusion. If this one comes and generates 0, it will say this does not satisfy. Is that right? So still, this one will also be false. Is that right? The same thing will still be for x being equals to 0. You see, right? So now we see that they will still be like that. Any question here? So these ones can change. We're going to be looking at these kind of questions from question papers which are multiple choice. Because they do bring multiple choice here, right? They do bring multiple choice in a test. You find out it's like 10 marks or 20 marks. So if you don't understand the theory behind, you might be lost. Yeah, any question?
Can you do the one in and they exist really true? Let's say or they exist y, and then they exist x such that xy is equals to 2.
I said they exist what?
They readily true delay they exist.
Oh, they exist x
just check
element.
the condition.
No, such that
Sure.
will exist y element of R. Such that xy is equals like this. This will always be true. Reason being this, the reason this will always be true is because you're the one who chooses. You say right now. You're the one who chooses. You choose the number. Let's say I choose 2 now. I can still choose 1. So that when I multiply this 2, I get 2. This one will always be true. You see right now? This will always be true. So I don't think they can bring a question that says they exist for both. If they do, they're just trying to see if you are really studying or not. They'll want to judge you there when they're marking. It's like they want to laugh at your script. If they bring a question like this, they won't bring this. You must screenshot. So yeah, we look at questions that they can bring, right? This one, so for they exist. If they bring it, just know that if that number, right, let's say they exist, obviously I'm going to restrict myself to a number that is there, and that will always satisfy it, because they exist says that you restrict yourself. You say, right? Then for all says that there's no restriction, you must check all numbers. So they exist, it can be at least one. There can be one number that will satisfy this. You say, right? And that is true. So any question? So if there's no question, it means that we can close this. Usually I only consider this two, and then we'll look at other ones in the next class. Yeah, so